To finish out this section, we're going to take a look at two theorems, one of which is the remainder theorem, the other which is the factor theorem. The remainder says that if we have a polynomial, if f at x is divided by x minus c, then the remainder is going to be the same as f at c. And so one way to be able to evaluate a function is to do polynomial division. And it's not always the most efficient way to do it, but it is a way to do so. So just to verify that this works, let's go through and we're going to evaluate f at -2. We're going to use polynomial division to evaluate f at -2, and then we're going to comment on the difference. All right, so letter A, really easy. Okay, this is way back from the beginning of the course. So this is f at -2, and that's going to be 5 times -2 cubed plus 6 times -2 plus 8. Now, if we compute this and simplify, that's going to be 5 times -8 minus 12 plus 8, or -40 minus 12 plus 8. And if we go through and compute that, that should be -44. All right, so let's hold on to that number, because now what we're going to do is we're going to go through and just do the polynomial division. Okay, so let's go ahead and do long division, or so we can actually do synthetic division right here, because we could just use this -2. Okay, so if I take my -2 and I'm just going to copy over the polynomial, so we're going to have a 5. Now notice there's no x squared, so I have a 0, a 6, and an 8. If I drop down the 5, that's going to give me -10 right here. And then 2 times -10 is going to be +20. Okay, and that's going to be 26. And then if I multiply that by -2, that gives me a -52. And then if I add those together, that gives me -44. And check it out. This is the remainder that we got. Okay, so in other words, we could say that according to the remainder theorem, f at -2 would be -44 by the remainder theorem. And of course, if we're commenting on the answers from part A and B, they're the same as expected by the remainder theorem. Okay, so we're going to say the results are the same as indicated by the remainder theorem. All right. So there are uses for this, and it's mainly a little bit later in mathematics when you start studying like abstract mathematics or discrete mathematics and doing some proofs. There's some pretty cool number tricks with this, but for right now, this is just illustrating, to use the remainder theorem, that you could evaluate a function. Okay. Now, there's also a factor theorem. Okay, and the factor theorem is actually going to be more useful to us, especially in the next section of the course where we start finding the zeros of polynomial equations that might not be as easy to find. So if f of x is a polynomial, if f at c equals 0, then x minus c is a factor. And if x minus c is a factor of f, then f at c equals 0. And what we're going to do is we're going to use this to be able to solve these sorts of polynomial equations. All right. Now, in this section, I'm going to give you some of the zeros. In subsequent sections, we're going to be able to find some of the zeros for ourselves. Okay. So let's solve each of the equations by using the given 0. All right. So we have this 2x cubed minus 3x squared minus 11x plus 6, and we're telling you equals 0. And I'm stating that x equals 3 is a 0. All right. So one of the solutions right away is x equals 3. But what that also means is that x minus 3 is a factor, right? And if it's a factor, that means what we can do is we can divide this. And what we're going to do is we're going to take 2x cubed minus 3x squared minus 11x plus 6. Not 110x, but 11x. Not sure where that happened, but 11x plus 6. And we're going to divide that by x minus 3. And since it's a factor, the remainder should be equal to 0, right? And we can use synthetic division here, right? So let's do so. So I'm going to stick the 3 on the outside, 2, -3, -11, and 6, and we're just going to divide this out. So we drop down the 2. 3 times 2 is 6. -3 and 6 is 3. 3 times 3 is 9. We drop down a -2. 3 times -2 is -6, and we have a remainder of 0. So what this means is that we can rewrite this equation at this point, okay? So what that means is, now let's go ahead and turn this into a polynomial. Remember, 2 is going to be the constant, 0 is the remainder, which doesn't matter. 3 is going to be the coefficient of x. 2 is going to be the coefficient of x squared. Okay? And so when we write this, what we can do is we can go back and remember that x minus 3 was a factor. But now we also have 2x squared plus 3x minus 2 equals 0. So what we did was we just divided that out. And that's the factor theorem. Okay. Now, another thing that we notice is that now we have a quadratic. And at this point, what we could do is we might be able to either use the quadratic formula, okay, or if even possible, we can factor the remaining trinomial. And that's exactly what we're going to do, right? So we have an x minus 3, that drops down. To build 2x squared, I have a 2x and an x. To build a -2, there's only 2 factors, okay? Those factors are either going to be 1 and 2 or 2 and 1. Now, I'm going to try 1 and 2, and we need a -2. So we need 1 to be negative and 1 to be positive. Since this is positive, I'm going to put the plus sign opposite the bigger number, and that usually works, right? And of course, if we don't trust this, we can FOIL this out, okay? So 2x times that is 2x squared. 2x times 2 is 4x. And then we get a -x, and then we get a -2. And that actually gives us what's above. All right, so that's a way that you can always check your factorization, is to FOIL it back out. Okay, and there's other ways to factor, all right, but that's just the way that's a little bit easier. And so now what we can do is we can finish by solving, because remember, we could set each of the factors equal to 0. Okay, so we have x minus 3 equals 0, 2x minus 1 equals 0, x plus 2 equals 0. One of the solutions we already knew was x equals 3. Another solution, we just subtract 2 from both sides and x is -2. Finally, we add 1 to both sides of this equation, and then we divide by 2. And so our final answer is going to be 1/2. Right? If we were to write this into the solution set notation, we could say x equals 3, 1/2, -2. One final example of this, exact same thing that we just did. This time we're saying that x minus 3/2 is a 0, or x equals -3/2 is a 0. And so that means that x plus 3/2 is a factor, right? And so what we could do is we could rewrite this problem as 12x cubed plus 16x squared minus 5x minus 3, and then we could divide that by x plus 3/2. Now, I know you're looking at this and you probably don't like the 3/2, okay, but it's okay. We can still use synthetic division on this, okay? So on the outside, I'm going to write -3/2. On the inside, I'm going to write 12, 16, -5, -3. Remember, the remainder should be 0. Okay, so when we're done, because x plus 3/2 is a factor, we should end up with 0 for our remainder. We're going to drop down the 12, and then 12 times -3/2, we could certainly use a calculator to do that. Okay, or another way to do it off to the side is we could just take -3/2 and multiply it by 12/1. We know 12 divided by 2 is 6. -3 times 6 is -18. Okay, so and let me write that up here, excuse me. So this would be -18. 16 minus 18 is going to be a -2. Now, if we multiply together, we have -3/2 times -2. Those cancel out. And then -3 times -1 is a +3. All right, remember this was a 5. So now we're going to drop down another -2. And then finally, -3 times -2, we already knew that to be 3. All right, and that's good because that gives us a remainder of 0. Okay. So now what happens is we can rewrite this, and we can rewrite this as x plus 3/2, and then we have 12x squared minus 2x minus 2 equals 0. Now, the last thing we're going to do is we're going to factor this if we can. All right, in this case, we can factor it, I believe. Notice that there's a greatest common factor of 2. Okay, so all the terms have a 2, so I'm going to factor a 2 out. I'm going to put it all the way out front. We have x plus 3/2, and then we're left with 6x squared minus x minus 1 equals 0. We know that 6x squared can be written as 3x times 2x. We need to get a -1, and we know the only factors 1 are going to be 1 and 1. Since this is negative, we probably want to put the negative opposite of the bigger x. So I'm going to put a negative here and a positive here. That should do it, but again, if you don't trust me, what you should do is FOIL this out, right? And I will FOIL it just to make sure it's okay. So this gives us our 6x squared. This is going to give us a -3x. This is going to give us a positive 2x, and this gives us a -1. And then if we combine these together, that gives us our -x. So it looks like that is the correct factorization, right? Now, of course, you can also use the quadratic formula to be able to solve this, okay? So what you would do is just use the quadratic formula, set it equal to 0, and just plug it in that way, right? To finish this off, we set each of the factors to 0. So x plus 3/2 equals 0, 3x plus 1 equals 0, 2x minus 1 equals 0. And then finally, subtract 3/2. And we already knew the solution to this one, -3/2. Over here, I'm going to subtract 1, and then I'm going to divide by 3. So another of our solutions is going to be -1/3. And then finally, if I add 1 to both sides and then divide by 2, I get x equals 1/2. All right. This would be a really tough equation to try to solve without knowing that this is one of the zeros. Okay. And of course, we just go down here and we check that. Okay. All right. So that's our factor theorem and our remainder theorem. The factor theorem helps us to be able to solve equations of polynomial types of equations if we know one of the zeros. Okay. Now, in the next section, what's going to happen is, what if we don't know the zeros? Okay. And we have a polynomial equation. That's where we're going to be able to use something called a rational zeros theorem. And we're going to learn that in our next video series.